with trigonometry is this concept of a right-angled triangle. Okay, so you take a right-angled triangle. This is very brief recording. I am recording this, so if you're not quite sure, I'd rather you paid attention than took notes right now. You can take notes, I don't mind, but I'm going to go quite fast with that. There's an angle which we call theta. Traditionally, we call angles by a Greek letter. Okay, so at this point, you know that that's the hypotenuse, that's the adjacent, that's the opposite, and you know that sine is the opposite over the hypotenuse, and cosine is the adjacent over hypotenuse. Okay, and you've done that before. Okay, you've done it quite successfully. It's not a problem. All right. Now, what we need you to understand is the fact that actually that was never true of a triangle. Okay, it applies to triangles. We use it in triangles, but you've got this fixed in your head that it's a right-angled triangle. Okay. Now, Pythagoras used right angles. So when we did the work last lesson on finding the height of a triangle and stuff like that, yes, you need a right-angled triangle to do that. But you're going to learn about trigonometry in a circle. Okay, so we're going to draw you some circles. Okay, so I want you to imagine you've got a circle. I want you to imagine that the circle has a radius of 1 meter. Okay, and I want you to imagine you are looking in that direction. So if I was to put my pen here, and I'm going to draw a circle with my pen, right, this is what I'm going to do. Okay, so if I now if I do it from the side, you should better see it a little bit more obviously. Let's go like this. I'm drawing a circle with my pen, but as far as you can see, if you only looked at, because you can only see in one dimension from my camera. Yeah, if I drew it in the air, you can see it easily. Okay, so we're going to look only from this direction, and I'm going to draw an angle here, which I'm going to call theta, and there's my height. So what's my hypotenuse in my little tiny triangle here? What's the hypotenuse? How long is it? Stunned silence. The hypotenuse must be 1, because I told you the radius of the circle is 1 meter. So if I take my pen here, and I zoom out a bit, and I take my pen and I spin my pen round in a circle, at that point, how long is the pen? Exactly the same as it was there. Yes? So no matter where I am round the circle, this length here is still exactly the same. So if we pretend that I've got a 1 meter long pen, okay, then when I get to there, how long is the pen? Still 1 meter. Are we understanding me? Okay, great. So we go back to my little circle then. I'll zoom in a bit for you so you can see what's going on. Okay. There. So if that was 1 meter to start with, that's still 1 meter now, isn't it? Yeah? So the sine of the angle, sine theta, is the opposite over the hypotenuse. But I've rigged things so that the hypotenuse is 1. Which means that that's effectively disappeared, because when you divide by 1, nothing happens, does it? So therefore, I've got the height of my circle. So the height here, the change in the height, because originally it was 0, yeah, hadn't moved, and now it's gone up a bit. Yeah, and the height will change depending on what I do. If I did it again with another angle, let's go for that one. Can you see I've got a little height? So the sine of this angle, the red one, is whatever the hell that is. And the sine of the blue angle is that one. Now what's the sine of 90 degrees then? Well, if I draw 90 degrees straight up, you're still looking from this direction. How high is my pen? It's 1. So we've already now established straight away that the sine of 90 degrees is 1, because I've got to the top of my circle. Okay? And we already established as well that sine of 0 degrees must be 0, because I haven't moved. Now the whole reason I'm doing this is because whilst you're used to angles only going up to 90 degrees, you know perfectly well that angles can go all the way up to 360. So, what happens when I draw the green one? So let's just, for argument's sake, say that that's maybe 130 degrees. What do you see from this direction? You see that height there. Now the fact that it's on the other side doesn't matter from your point of view, because again, if I turned everything on its side and I did this for you, there I go. Oops, actually I've zoomed in a bit. Zoom out. So from your point of view, here's my circle going round in a circle. The people to this side of me can quite clearly see I'm drawing a circle. But if you're looking on the screen, what you're really seeing is this. There's no real difference between that and that. Okay? Now the whole reason I'm showing you all of that is because actually we can use trigonometry with an angle bigger than 90 degrees. It's quite easy. I've already established that to you quite clearly by talking about the fact that the opposite is this length and the hypotenuse is still 1, isn't it? So I can actually have lots of different scenarios going on at once. In fact, I can have an angle of 270 degrees down there. Please tell the person sitting next to you what you think's happened to the height. What's happened to that height? It's become negative. Yes. Because if that line there was 0, watch, as I go round the circle, the person looking from the eye has seen the line go up. It gets up to the top, and then as the angle gets more than 90, it starts to come back down again. Once it gets to 180, we're back to 0 again, aren't we? So now we go to 181, we're now starting to go down. So from the person looking at this end, person looking that way, we've now gone down. So actually we're going to negative. And in fact, when we get to there, what's the person going to see? -1. And then back to 0. Now if that's confusing you a bit, can I suggest very strongly that you access the video and watch it a few times, because it does make sense. We go, as we go round the circle, what you see goes up, comes back down, and becomes negative, and comes back up again. So if we're going to draw a graph of that, and this is called a sine graph. Okay, so we're going to draw a nice, neat, tidy graph. So here's my axes. So if I went round the circle 0 degrees, so let's go up to 360 here. Let's do some key points, 180. Let's do here 90. Let's do here 270. Let's go here for say 45. Yeah, so if we go 45 again, we've got 135. And so on and so on and so on. At 0 degrees on my circle, so here I am. I've not moved around my circle at all. So there's my 0 point. You see the line at 0. At 90 degrees, okay, we established already, I'll just flip it over for you so you can see. We established that at 90 degrees, we were straight up and down, therefore you'll see 1. So on my graph here, I'm going to put a little number 1 up here. So at 90 degrees, I get to 1. At 180 degrees, what happened? Come on, don't be dumb. I went up to 1, 180 degrees around the circle, I'm now back to the middle, aren't I? So 180 degrees, I end up at 0. Remember, I started at 0. Yeah? Now, if I started at 1, then I'd have had to go up to 2, wouldn't I? So I'm starting at 0 because it's easier. Right, so at 270 degrees, which is 3/4 of the way round, so if I start here and I go round, that's 90, that's 180, so right at the bottom, that's 270. What do you see from this side? You see now -1, because it's right at the bottom. So on my graph, I can now put a little -1 there. Okay? And then as I go round and keep going round to 360, I'm going to end up coming back up again to 0. So what I'm going to get is a graph which looks a little bit like this. I'm going to take some time to draw this carefully, if you don't mind. and that's called a sine curve. And that's what it looks like. Okay? Now, for those of you going up to 90, it's still exactly the same. Like the sine of 30 degrees is a half. If I put a little 30 there, hope you can see that I'm about a half. Yep? And so on and so on and so on and so on. Okay? But what I'm trying to point out to you is that the sine of 30 is a half, I agree. But the sine of 150 is also a half. And that makes sense if you look at the circle. Yeah? Because if I draw a line there, so that's 30 degrees, that's halfway up. So if I draw a line 150 degrees all the way around, it'll be the same point on the other side. But as far as you're seeing, all you're seeing is the pen going up and down. So it's the same from your point of view. And all I'm trying to establish in your mind is the concept that sin, cos and tan actually work for angles bigger than 90 degrees. And the only way you can have an angle bigger than 90 degrees is if it's not a right angle triangle. Because it can't possibly be a right angle triangle if you've got angles of 110 degrees. You can't have it. So you just need to understand the fact that sin, cos and tan work like that way. Now, that's a sin graph. A cos graph works in exactly the same way, but cos isn't the opposite over the hypotenuse, it's the adjacent over hypotenuse. We established that at the beginning. Again, get used to the way the videos work. I go very quickly. You can scroll backwards and forwards through the video as many times as you like, can't you? So all that's going to change is instead of looking at the height, we're looking at the base. So we look from this point of view for cos. That's where we look for cos. So when I'm at 0 for my angle, cos is now 1. When I'm at 90 degrees for my angle, cos, looking from the bottom, is now 0. When I'm at 180 degrees, cos is now -1. When I'm at 270 degrees, cos is now 0. So a cosine graph, so I drew the sine graph in green, so in blue, here comes the cosine graph. And it's absolutely identical, except that it starts in a different place. Because instead of looking from the side, we're now looking from the bottom. Okay, so the green one is a sine graph, and the blue one is a cosine graph. Okay, now all I want you to worry about the facts is, first of all, make sure you've seen that and you understand what's going on. And now accept from me that what we're going to be doing for the next few days is looking at trigonometry with triangles that are not right angles. Okay?